Hello everyone. So today's video is about carrier recombination and generation. There are 5 subtopics that will be explained. The first one is recombination generation model. Second one is band-to-band recombination. The third one is trap-assisted recombination. And the fourth, surface recombination. And the last one will be Auger recombination. So what is recombination? Recombination is the mechanism that is utilized by the extrinsic semiconductors to equilibrate excess charge carrier through the bringing together and annihilation of oppositely charged carrier. And carrier generation is a process where electron-hole pairs are created by exciting an electron from the valence band and the semiconductor to the conduction band, thereby creating a hole in the valence.
A simple model for the recombination generation mechanism states that the recombination generation rate is proportional to the excess carrier density. So, the following expression is for the combination of electron p-type semiconductor. And similarly, for holes in n-type semiconductor, where the parameter T can be interpreted as the average time after which an excess minority carrier recombines. We will show for every one of the diverse recombination components that the recombination rate can be streamlined to this structure when applied to the minority transporters in a semi-non-partisan semiconductor. Thus, the recombination pairs of the greater part transporters relies upon the abundance minority transporter thickness, as the minority transporters limit the band-to-band or radiative recombination is a reverse process of photon absorption where an electron drops back down to its equilibrium energy band and radiates a photon. In thermal equilibrium, the recombination rate is balanced by an equal and opposite generation rate, and so without any extra stimulus to generate free charge carriers above equilibrium, the net equilibrium recombination rate U is given by the total recombination rate minus the equilibrium.
Trap-assisted recombination. Trap-assisted recombination occurs when an electron falls into a trap, which is an energy level within the band gap caused by the presence of a foreign atom or structural defect. The electron occupying the trap moves into an empty valence band state, thereby completing the recombination process. There are two domain trapping models. The first one is Shockley-Red Hole model, which is the default one, where the electron in transition between bands pass through a new energy state created within the band gap by a dopant or defect in crystal lattice. Such energy states are called traps. The second one is explicit trap distribution. This option allows the specification of number of discrete traps or a continuous density trap states at energies within the band gap. Degrees of freedom are added to the equation system to represent the occupancy of trap at a particular energy. So here is the visual of three different recombination. We focus on the middle one, which is the trap-assisted recombination. We can see the electron are trapped into the energy band gap. These are the formulas that can be used to find the net recombination rate for trap-assisted.
What is the surface recombination? Trap-assisted recombination at the surface of a semiconductor is referred to as surface recombination. This occurs when the trap at interface of the semiconductor forms due to the dangling bond caused by the sudden disconnection of the semiconductor crystal. In applications such as solar cell, surface recombination may be the domination mechanism of recombination due to the collection and extraction of free carrier at the surface. So, this is the example of the surface recombination. A back surface field BSF consists of a higher dop region at the rear surface of the solar cell. The interface between the higher and the lower dop region behave like a p-n junction. The carrier concentration is thus maintained at the high level in the path of the divide, and the BSF has a net effect of the preserving the rear surface. This is the example of the band.
Auger recombination is a process that is identical to radiative recombination, but the Auger recombination, on the other hand, provides the energy to another carrier rather than releasing it as a photon. A non-radiative recombination event occurs when two electrons collide in the vicinity of a hole. The second electron absorbs the energy and momentum. This electron or relax the excess energy and momentum to the photon and is called thermal relaxation.